Hello everyone, today we're going to be working on fundamental problem 7.3, and this problem is asking us to determine the normal force, shear force, and moment at point C. So the first thing that we're going to do is we're going to draw out the cut at our point C, and then from there we're going to analyze both our left and right side of the beam to see which side of the beam would be easier to work with. As you guys could see on our left side, we have a distributed weight of 3.6 cube feet for a span of 6 feet. And then from there at point A, we have a roller support, meaning we would have to determine the value of one vertical reaction. Meanwhile, if we were to work with our right side, we could see that at point B, we have a pin support, meaning we would have to determine the value of two unknown reactions. And because of that, I will be working with the left side since I would just have to find the reaction at point A. So before determining the value of my reaction, the first thing that I want to do is I want to take this distributed weight and find its concentrated force. So to do that, what we're going to do is we're going to call that force our concentrated force, or we're going to name it F1. And to determine the concentrated weight, what we're going to do is we're going to take our distributed weight, which is 3.6 cube feet, and multiply that by the span of 6 feet, because as you guys could see, this distributed weight is for the span of 6 feet. From there, we should get our concentrated weight, and we end up getting a value of 21.6 kips. Now, as for the location of that concentrated weight, as you guys could see, this concentrated weight is in a uniform loading. It is, I guess you could say, it's in the shape of a rectangle. And because of that, we know then that since it's in a rectangle, it's a uniform, constant weight. We know that our concentrated force will be found right in the middle of that span. So we know that it would be 3 feet from the roller support. We know that it's 3 feet out. And then from the end of the beam, we know it's 3 feet in. So right here at the 3 feet mark is where we will find our concentrated weight. That's where we find our F1. So now that we have our concentrated force, now we can determine the value of our reaction at E sub y. Since it is a roller support, we know it's going to be a vertical reaction. So we have to right now assume if it's going to be going upwards or downwards. I'm going to assume that it will be going upwards. And we're going to name it A sub y. So from there, to determine the value of our reaction A sub y, what I'm going to be doing is I'm going to be taking the sum of the moments about point B, because that way, when taking the sum of the moments about point B, we know that the two reactions at our pin support will not be creating a moment, meaning that we would simply be able to solve for our reaction A sub y. So sign convention counterclockwise is positive. The sum of our moments in our point B have to equal 0. So from there, our two forces that will be creating a moment is our reaction A sub y and our concentrated force. So our reaction A sub y, we know that it's going to be creating that clockwise moment, meaning a negative moment. So that's a negative moment with a force. That's what we're trying to determine, times the distance. We know that from our reaction and our other reaction, there is a span of 4.5 feet plus 4.5 feet, giving us a total of 9 feet. From there, we have our concentrated force, our F1. We know that it is going downwards, so we know that about point B, it will be creating that counterclockwise moment, meaning positive moment. So we know we're going to get a positive moment from that. We know that the force of our concentrated force is of 21.6 kips. And then from there, the span or the distance from our concentrated force to the to point B, we know that from here to here, there's a span of 9 feet. So 9 feet plus from here to here, we said that our concentrated force is located right at the middle. So the middle of 6 feet is 3 feet. So we have 3 feet here to here plus the 9 feet, which gives us a total of 12 feet. And we know that all of that has to equal 0. So from here, we would simply just be solving for our reaction A sub y. So we would end up getting that A sub y is equal to 28.8 kips. And since we got a positive number, that means that it will be going upwards. So now that we found out the value of our A sub y, the next step that we're going to be doing is now drawing our free body diagram of our beam with the side of the beam that we will be working with, which in this case would be the left side. So our free body diagrams would be our next step. So we would draw out our beam, the left side of our beam in this case. We have our distributed weight. From there, we know that midspan, we find our concentrated weight of all that distributed. From there, we know that we have our reaction at our point A, so which would be right here. I'm actually going to draw it in blue. With a value of 28.8 kips. And then from there, that should be everything. So from there, I'm just going to be drawing out our dimensions. So we know that from the end of our beam to the reaction, we have a span of 6 feet. But we know that from here to here, we have a span of 3 feet from our concentrated force to our reaction. And then from there, we could now draw our cut, which is right there. We know that from our reaction to our cut, there is a span of 4.5 feet, sorry. So now that we have that, we can now continue to draw out our normal force, shear force, and moment. So remember, this is where our sign convention comes in. Since our cut is to the right side of the beam, that means that our shear force will be acting downwards. But we know this because of our sign convention. We're going to denote our shear force with the letter V. From there, we know that our normal force will be going away from the cut. So in this case, to the right. We're going to denote that with the letter P. And then from there, our moment, based off of our sign convention, we know that it will be going counterclockwise. And we're going to denote that with the letter M. So now that we have everything to determine the values of our normal and shear force and moment, we're simply just going to be taking the sum of the forces in the X and Y direction and the sum of the moments about the cut. So I'm going to start off with my normal force by taking the sum of our forces in the X direction. And as you guys can see, our normal force is our only force in the X direction, or a horizontal force. So we know that our normal force will have a value of 0, since it is our only force in the X direction. From there, we're going to take the sum of the forces in our Y direction. As you guys can see, we have our 21.6 concentrated force from that distributed loading acting downwards. So that means negative 21.6 kips. From there, we have our reaction of 28.8 kips, so that's positive 28.8 kips. And then from there, we have our shear force that, based off of our sign convention, we know that will be going downwards. So that's a negative force, so negative shear force. We know that all of that has to equal 0. So from here, we would just simply solve for our shear force, and we would end up getting a value of 7.2 kips. So with that, we have determined the value of our shear force. And then from there, to determine our moments, what we're going to do is be taking some of the moments about the cut or about point C, however you want to say it. So sign convention, counterclockwise positive, the sum of our moments about the cut. We know that they have to equal 0. So we know that since we're taking the sum of the moments about the cut, that our normal force and shear force will not be creating a moment. So the only things that are creating the moment is our distributed loading and our reaction. So we know that our concentrated force of our distributed loading about the cut will be creating a counterclockwise moment as well. So that means it's going to be a positive moment. We know that it has a force of 21.6 kips. And then we know that the distance from the cut to here is, we know that from here to our reaction, there's a distance of 3 feet. And then we know that from our reaction to the cut, there is a distance of 4.5 feet. So we know that there is a total distance of 7.5 feet. From there, we have our 28.8 kip from our reaction. We know that's going to be creating a clockwise moment, meaning a negative moment, with a force of 28.8 kips. From there, we multiply that by the distance. So we know that from our reaction to the cut, there is a distance of 4.5 feet. And then from there, our last moment is our moment, which we know it is going counterclockwise based off of our sign convention, so a positive moment. We know that all of that has to equal 0. From here, we would simply just be solving for our M, our moment. So we would end up getting that our moment is equal to 32.4 kip feet. Sorry, negative 32.4 kip feet. And with that, we are done with our fundamental problem 7.3. So once again, this problem was asking us to determine the normal force, shear force, and moment at point C. So since it's asking us for a specific point throughout the beam, we're going to be cutting right where it asked us. So we cut the beam right at point C. From there, we analyzed both sides of the beam to see which one would be easier. From there, since we were dealing with the left side of the beam, I found the concentrated force of that distributed loading as well as where it was going to be located. And after that, I was able to determine the value of our unknown reaction that we had. From there, I proceeded to drawing out a free body diagram. And after I added our shear and normal force and moment based on the sign convention. And then from there, I simply just solved for our normal and shear force by taking the sum of our forces in the x and y direction. And then to solve for our moment, I just took the sum of the moments about the cut. Thank you guys so much for watching this video. Please feel free to give this video a thumbs up if you found this video useful. And please feel free to subscribe to our channel if you guys would like to see more videos like this.